I want to next look at another piece that comes up when we talk about how classes are interacted with. Namely, I want to talk about super. Let's take a look. Let's first think about how protocols are generally implemented in Python. If we are using composition, generally, what we'll do in Python is we'll have some composed object, and then we'll implement the protocol by delegating the work back to the composed object. We don't define from scratch what len means. We say, if you're asking me for my length, we'll ask my constituent object self.data what its length is, and that's my answer. And maybe we'll play with this a little bit. We'll, do something with the return value here. We might intercept it. But for the most part, you can see the bulk of really defining what it means to get the length of this, the size of this thing, is being delegated to self.data, which may then further delegate it down the line. If it's a case that we're not using composition, but we're instead using inheritance, then what we might do is we might delegate this to a base type. So here you can see if B inherits from A, we might say, you know what? My len is actually whatever the A length is, and I'll do some small modification of it again, something like this. Well, this is generally the approach that we might take. We want to delegate the bulk of the work so that when we implement a protocol, we're just doing the small incremental thing that we know is specific to the type that we're working with. And the bulk of the work is being handled by somebody else who may delegate to somebody else, who may delegate to somebody else, which may delegate it to an ultimate definition on the object type or on one of the built-in types. Well, let's consider what happens when we have multiple inheritance and see why it's important to know about one aspect of all of this, the MRO. Here, I have multiple inheritance. B and C inherit from A, and D inherits from B and C. And at D, when I do the D call, I'm going to call B's call and C's call. I'm going to call A's call, and an A, it's where I terminate. So what I'm going to do is I'm going to say the work that I need to do to implement this call also involves work that was previously implemented on my subtypes, and I need to include all of these together. And so I'll manually invoke the call method on my subtype. And so when we see this in play, we can see when we call this call method here on the object, we get D's, then B's, then A's, then D's again, then A's, then C's, then A's, and it may turn out that we get A's twice here. Check. That's good. Twice here. So we get D, B, A, C, A, and it should, wonder why it doesn't give you the A twice there. Well, we can take a look at that separately. Oh yeah, because as a consequence of the way this works, here the C is calling the A and the B is calling A. So we would only see A twice, once after the B and once after the C. And this is the problem that we might see. We might say, you know what? I don't really want to invoke this method twice. I don't know if it's safe to invoke or if it's proper to invoke this method twice. Really, when I want to invoke call, I want to invoke it on each one of my base types. I want it to invoke it once on C, once on B, and once on A. And hard coding where to go next just isn't working for me. Let's talk a little bit about what happens in multiple inheritance before we talk about how we can solve this problem. Here we have the actual inheritance hierarchy, A and B and C inheriting from it, and D inheriting from B and C. And at each level of this, we can kind of see what we expect the inheritance hierarchy to look like. A expects it inherits from object. B expects it inherits from A, an object. C expects it inherits from A, an object. And so I guess D expects it inherits from B and C, and also A, an object. And when you look at this, you can see that it's possible for us to create a linear ordering with no repetition, which respects the ordering at every possible level. In other words, when you look at this, you can see if I consider my predecessors at the level of D to be D, B, C, and A, then at every level, I'm assuming the same ordering that's assumed at a level higher. See, it's always A object, it's always B, then A, then object, then C, then A, then object, and it's the same thing here. I'm just figuring out how to interleave these to preserve that ordering. And so, completely valid for me to define this class in this fashion, and in fact, you can see I could define the class either with D of C and B or D of B and C. There really isn't much of a difference either way. However, if I did a very slightly different inheritance hierarchy, we can see that there could be some problem here. Here, I have A or B inheriting from A, C inheriting from B, and D inheriting from B and C. And you could see where, if I set up this hierarchy wrong, I could have a conflict in the order in which things view themselves in terms of what they precede and what they succeed. Here, A says I'm before object, B says I'm before A and before object, C says I'm before B and A and object, but D says B comes before C. You can see there's a conflict here. One of these levels says that C comes before B, and the other level says B comes before C. And Python cannot reconcile these. And in fact, Python will give you an error and say there is no consistent way to reconcile these, to have every layer of this say what its base classes are in a strict linear ordering, which preserves a common understanding of who precedes who. This is what the MRO is. It's the consistent ordering for who precedes whom that then gets used for things like method resolution and super resolution. What you can think is, if I were to swap the order of my inheritance here, instead of BC, make it CB, then I no longer have that discrepancy. And Python would actually allow me to have this hierarchy if I inherit D from C first and then B second. And you can think that the ordering that you see here visually is going to have to match the ordering that you consider here, because otherwise that would make no sense if you know the difference between D of CB and D of BC wasn't something that you could rely on in some meaningful fashion. If you couldn't say, oh, this gives B precedence over C. This is what the MRO is all about. You can see Python actually prevents you from creating classes where it can't create a consistent MRO. Well, the MRO tells you the order in which you should go if you want to go to the base class and you don't want to repeat anything. You want to just linearize this in a single list where every element is unique. And so you can see the MRO for D is D, then the B layer, then the C layer, then the A layer, then the object layer. And you can think this is probably just some sort of topological sorting of these, you know, on the dependencies from, it's a level ordering on the dependencies from the highest level to the lowest level. If I invoke a method or if I ask for an attribute on D, as we'll see, not here, but in a future session, as we'll see, this actually follows the MRO to decide where it's going to look. It first looks in D, then in B, then in C, and then in A. Well, if I wanted to do this delegation to my base class, what I really want to do is I want to delegate to the base class according to the MRO. And that is what super gives me. Super gives me the ability to delegate to my base classes along the MRO without the repetition that we saw previously. And so here I have two classes, A and B. And I want to show you something first, very quickly. Here I have a class B that inherits from A. And this is a very important consideration before I show you the MRO example. Remember, in Python, there is never a confusion between what your runtime versus your compile time classes as there would be in, say, C++ or Java. In Python, everything exists at runtime, and everything, you know, that interesting happens at runtime. So as a consequence, you always know what your runtime type here. You know, when you're in this A method, you're still an object of type B, even though this is the method in the class A. There really is no distinction, or there is no confusion, rather. And so it's not the case that at this level you might think, oh, I'm of type A. No, you know what your runtime type is. And in fact, you can see what your runtime type is. You just do type of self, and you can see that's exactly what you'd expect it to be. It's really, unlike in some other languages, there really is no confusion here. What you can, however, do in Python that's a little bit surprising is you can tell a class, notice there is no inheritance hierarchy. You can tell a class that it's a different class. This class attribute is actually how Python determines what the type of some instance is. And it determines how Python figures out where the attributes are, which MRO to follow. You can actually mutate this. So you can take an object of class A and then tell it, no, I decided you're of class B, even though A and B have no relationship whatsoever. You can actually do runtime casting of Python objects in this fashion. This is one of only about 2 places in Python where you can actually do something akin to a cast. Well, getting that out of the way, I want to talk a little bit about how super works. What happens when you invoke super is you just go down one step down the MRO. And this allows you to visit every single base type in a strict, consistent linear ordering without repetition. And so my super call just says, okay, using myself and knowledge that I'm at D, where do I go next? Using my runtime class state and knowledge that I'm at C, where do I go next? Using my runtime class state and my knowledge that I'm at B, where do I go next? And you can see why these 2 arguments might exist. You could imagine that the super call kind of looks something like this. class in the instance, and it's probably doing something like asking the runtime instance for its actual MRO. And then it's doing something like asking the MRO, where are we right now? And then it's going to say, okay, create some delegating object that just takes you one step further down the MRO. Something like that. And then it uses that in order to figure out how to dispatch. Really, this is why super takes those two arguments. It needs to know where it is right now, and it needs to know what the runtime type is, so it can figure out what that MRO is, so it can figure out where the next step will be. However, people got really irritated by having to write super with two arguments over and over and over again and having to repeat the class name here and here. And so one of the very few pieces of magic that exists in the Python parser, we actually have a no argument version of super that automatically determines how to figure out where you are next. You can actually do super without these two arguments, and it'll work just as well as if you pass those two arguments. And what's happening behind the scenes is this super call is doing a little bit of magic. It's closing around a special variable that's created only when the Python parser sees that it's evaluating a function body within a class. And what that means is when you do this super call, you can see that works. But what that means is if you were to try and call the super with no arguments outside of a definition in a class body, it won't work. This is, as I said, one of the very few pieces of magic that actually happens in the Python parser, figuring out how to fill in that class cell based off of where something is defined. And this is the one place where it really actually makes a difference if you define this in the class body, where Python will know, oh, I'm in a class body, therefore prepare that class cell so that it could be used by super later, or here where it can't tell that it's going to be brought into the class body separately, and it can't figure that out. And this is why some types of object construction type, metaprogramming may not always work the way you want. Things like super, you need to be a little bit careful about how you go about using them. Of course, the other solution here is you do some kind of binding here. So you do like this, and then you make this bind of A, and then you call this with, the class and the instance. So really not that hard to worry about. If you really wanted to worry about it, you could do something like that. Except this needs to be after this run. So you'd have to symbolically then delegate this on a metaclass. You need one more step because this B doesn't exist until after this line of code is written. You have to do a little bit here. The other stupid thing you could do is you just do something like this. This won't actually work because you never know if this is in the scope that you want, but you get the general idea. And you can kind of get around that if you need to do some metaprogramming, but this is why that comes up, because you have this one small piece of magic that exists in the parser. I want to show you one of the other very small pieces of magic that exists in the Python parser. As I said, the parser doesn't really do that much that isn't just execute a line of code, execute the next line of code, execute the next line of code, execute the next line of code. Rather, the Python parser and compiler combination don't do much more than that. The only really magical things they do are the super the no argument super, name mangling, and something we'll talk about in just a moment. Let me talk about what name mangling is all about. It may be the case that if you have some inheritance hierarchy, in this inheritance hierarchy, you might want one of these layers to delegate back up to the upper layer. So you want B to delegate back up to A. So when you call this call method, it calls B and then A. Fine. You may want there to be a function that exists at B that it's going to call here. But if this function can be overridden, then what you see here is this class, when it calls self.f, it's going to call this self.f. So we get b.f. Great. When we delegate up to the superclass, and here we see a self.f, the person who wrote this code might say, well, it's going to call this thing right here. But it's not, because this thing got overridden when you were inherited. And so you can see b.f got called twice. We don't have static isolation of these classes. And one thing that you might want to do, especially if you're doing some sort of multiple inheritance for a mix-in pattern, is you might want it to be the case that when you call a method in this source text, you know exactly what method it is, and you know that method is not going to be overridden later. So what you might do is you might say, you know what, I'm going to call this a_f, and then I'm going to tell people, please don't implement any methods named a_f. In fact, I'll even call it double_a.f to really make a point of telling you don't implement a method called underscore a.f, I'm assuming that this is a method that is never overridden. Well, that's exactly what name-mangling actually does in Python. Anytime the Python parser is parsing some code in a class body and it sees a variable name with 2 underscores prefacing it, it mangles that name. It changes this name for this attribute lookup to look something like this. Now, you can't really say for certain what it looks like. The mangling is not really supposed to be something that you're supposed to rely on, but more or less it's mangling it to something that looks different that will not be overridden later. And if I call this function underscore underscore f, then what you'll see in this case that is distinct from the previous cases, when each one of these layers wants to call its statically, lexically local underscore underscore f, it works. Here I have b.f and a.f, and this thing here did not override this thing here. The name mangling is one of the mechanisms that we can use to prevent later classes from overriding, which then loses our ability to locally reason about what some code does by looking at this block of code and saying, I don't need to know where else this thing is inherited from in order to understand what's going on here. The name mangling is somewhat limited, and it is a somewhat simple mechanical mechanism. Any underscore underscore x name, even if it's not an attribute, gets mangled. So here, if I say some local variable underscore underscore x equals 1, 2, 3, that gets mangled too. It's going to make a big deal. Well, no, it's going to be consistently mangled everywhere, but every underscore underscore x is mangled, and this requires that the parser can see the mangling. If I did something like this, get attr self underscore underscore x, this will fail. And the reason it'll fail is the Python parser cannot see that this is could be arbitrarily computation. So it can't see that this is a name that could be mangled. It doesn't know that that's the case. And so you'll see that that get attr is not mangled, whereas the static access is mangled. And so here, if we actually run this, this will fail. You have to be aware that the mangling has those rules. If you have underscore underscore methods, and they're not part of the built-in protocols or your own custom implementation of them, you have to make sure that you don't use something like get attr, because otherwise you won't be able to do the mangling. Of course, and there's really not much you can do about this. I guess you could do something really terrible, like you could do this equals object, and then you could look at your locals, and you could figure out, x, k for kv in locals.items. If v is x, and that gives you the name of it, and then you can figure out what the name is. Maybe, I don't know, does that give you the name? But in general, the name mangling presents you with a very small limitation here. Yep, there you can see that's what the name is. Then you could do your, your get attr on that name. If you really, really needed to do a get attr, you might have to do something like that. And here, this should be, let's get the first one that we see. There's something there. So you could do something like that if you really had to. What this also means is, if you define functions outside of class bodies, they won't get mangled. You can see here there's no mangling. The mangling is one of the things that the parser does only under that circumstance. Generally, the Python parser and compiler, they work very consistently. They work identically, irrespective of where you are in your Python source code. And this is one place, in combination with things like the zero argument super, where that is not met. So you can see here, this will not mangle at all. And you can see that if you had 2 classes with the same name, they're going to get mangled. The mangling rule is very simplistic. It's just the underscore and the name of the class, then 2 underscore, then the name of the attribute. So if you happen to have 2 classes with the exact same name, they'll mangle identically, which means you have to make sure that the underlying classes themselves have unique names so the mangling doesn't override itself. Because otherwise, you can see here, the overridden version is being called in both places because they mangled identically and it still overrode. So it's a very simplistic mechanism that you might have to be a little bit wary of if you need to. Here's what I want you to consider as our conclusion. When you are employing inheritance, you need to think about how the pieces of that inheritance compose, how those pieces fit together. And one of the ways that pieces fit together is you're sometimes delegating to the behavior on a base type. And in order to do that, you need to use super. In order to understand how super is actually doing the delegation, you need to understand the method resolution order, the MRO, as you need to do when you're doing method resolution, when you're doing attribute lookups. When you're trying to compose different classes in an inheritance approach, well, sometimes you want to do some sort of isolation. You want to isolate some behavior to the source text so you can see in front of you, and that's where you might want to use something like name-mangling. And when you want to use super and you don't want the pain of having to write the 2-argument version of super, you can make use of some of the magic the Python parser does to automatically supplement or to automatically provide that class cell that gets picked up by the super function.